Today we want to look at double integrals in polar coordinates, the way we're going to think about it, and the issue that arises and how we deal with that issue. So let's quickly review double integral in rectangular coordinates. The way we're thinking about this is that we're thinking about the function, the value of the function of being the height. We're thinking of the height multiplied by the area. And the area is going to be broken down into an iterated integral with a dx dy or a dy dx. The base model problem that we've been working on is that dA is a small piece of area, and it is made of a small piece of length and a small piece of width. So dx is a length and dy is a width, or the other way around. The names aren't that relevant. So that's our review of thinking of what the integral represents. The r, of course, is just all the values of x and y that we're going to plug into the expression. But although these three things can represent different quantities, our base model problem, we have a height multiplied by area. The area is length times width. All right. So this is when we are dealing in rectangular coordinates. So if I have a rectangular coordinate system, I mark locations in space with two different distances. And we say the coordinates there are x, y. I am marking that location with two different distances. Polar coordinates work differently. In polar coordinates, I use one distance and an angle. So this location in polar coordinates still has two coordinates, but only one of those coordinates is a distance. The other coordinate is an angle. So I would mark this location as r theta. We're in two-dimensional space. That means we're going to need two coordinates to mark a location. In three-dimensional space, whatever we're using to measure, we're going to need three of them. In four-dimensional space, whatever we're using to measure them, we're going to need four different coordinates and so on. So the point is that when I write dA, the area, that's going to be a length times a width. Both the dx and the dy are representing distance. So in this scenario, both dx and dy are distance. So dx dy is area. The problem here is that when we have a function in polar coordinates, only one of the coordinates represents distance. The other coordinate represents an angle. So dr times d theta is not going to give us an area. So in polar coordinates, r is distance, but theta is an angle. This is the issue that we need to deal with today. R is a distance, but theta is an angle. The reason that this is relevant is that if I write dr d theta, that doesn't represent an area. So when I write the expression dr times d theta, this is not an area. So what this means that d theta dr on its own does not represent area. I've got one distance multiplied by not a distance. So d theta dr does not represent an area. Because d theta is not distance. dr will represent some number of meters. D theta will represent some number of radians. So I'm not getting an area. I'm not getting meters squared. So this is the issue. We need to write this in such a way that d theta is distance. So we need to make d theta distance so that dA can be area. So let's take a look at what's going on. Let's take a look at what our little dr is and what our d theta is. So d theta is going to be some small piece of an angle. So one of the issues that we run into is that d theta is going to look gigantic in this case, but let's just say we're really far away. So here's some polar coordinate graph paper. I know the green line is a little bit wonky, but what we want to do is break the region up into small rectangles. We're going to break the region up into small rectangles, although we're not going to have rectangles because we're using polar coordinates. They're going to be a little bit bent. What we want to notice is that if I have some little piece dr, dr represents a distance. There's dr representing a distance, but the d theta is way back here as an angle. And this is what I want to call dA. Here's what we notice. dA is not exactly a rectangle. DA is not exactly a rectangle because of that curved side, because we're in polar coordinates. So first thing to note, DA is not a rectangle because of the curvy side. But we're going to do our usual calculus thing. If d theta is really small, then it's not going to be that curvy. Same thing that we did, the same kind of thinking that we did when we were finding area under a curve. Our function is continuously variable, our length is continuously variable, but if we make the dx small enough, then the function isn't going to change that much. Same kind of thing here. It's very hand-wavy. Now I'm going to draw another rectangle using the same dr and d theta, but I'm going to put it in a different location. So let's draw another rectangle. That was in quotes. It doesn't sound like it was in quotes, but I assure you, when I said it, I said rectangle in quotes. See, listen to the difference. Rectangle, rectangle. See how different they are? So out here, I'm using the same dr and the same d theta, but dA is much bigger. Same dr, same d theta, but further away, dA is a bigger area. So that's what we want to observe, is that dA is larger when we are farther from the pole. So what we want to look at is the arc length. And we're going to use the length of the arc as one of the dimensions of our rectangle. Once again, I don't know if you could hear it yet, but I said that in quotes. We're going to use this arc length as our rectangle. So just like circumference of a circle, where the circumference of the circle is 2 pi times the radius, the arc length is going to be 2 pi times the angle. The reason we get 2 pi times the radius is that 2 pi is the angle if we go all the way around the circle. So this arc depends on how far we are from the pole. So when we are r units from the pole, that will determine the arc, the length of that arc. So d theta is the angle, and just with like with circumference, and we just multiply by the radius. So it turns out that the length of that arc is proportional to the distance from the pole. If you're twice far away, that arc will be twice as long. And that constant of proportionality is just the other. So that is how we take d theta and turn it into a distance. We multiply by the radius. Notice that the radius will have distance units attached to it, multiplied by just radians, don't have any units. That will make that factor a distance. That's how we take d theta and turn it into a distance. Either one. Remember, we're going to make dr. dr is going to be infinitely small pretty soon. Once we start the integration process, dr is infinitely small. So it's wherever you happen to draw it. I guess if we want to be really pedantic, I'm drawing it to the inner parts because we usually frame things as like in the derivative f of x plus h minus f of x. And so h is that little extra delta. But the dr is going to be squishing down. So if you're going to draw all sketchy like me, then it doesn't really make a difference. But if you're going to draw carefully, I guess it should go to the nearest part. So just a quick reminder that this arc is just the smaller angle for a whole circle. So if we look at the circumference of a circle with a radius of r, the circumference is 2 pi times the radius. And the angle, it's just the angle times the radius. And the angle just happens to go all the way around. So all we're doing is instead of going all the way around for a 2 pi for the circumference, we're just doing d theta, a very small piece of the angle. So in polar coordinates, we're going to be setting up our double integrals slightly differently. We're going to need that extra factor of r as part of the dA. So f of r theta, that's our function, that's our height. And we'll be multiplying by a dA. That's going to be our area. But our area is going to look different. It's not just a dr and d theta. It's got an extra factor of r. Because I still want this to be a height multiplied by an area. But the dA is going to have an extra factor of r. Just writing dr d theta, you're not making an area. So if we write dr times r d theta, that turns d theta into an area. So in polar coordinates, the dA is going to have a factor of r times d theta. And then a dr. dA is r d theta dr, or r dr d theta. dA just pulls an extra factor of r. Now, in the construction, that r is part of the dA. When we go to integrate it, it's part of the function that we're integrating. So r in the construction is part of the dA, but when it comes to integrating, that's still a factor of r. It gets integrated when we go along with the function. So in construction, the area, the r goes with the area. That's how we're thinking of it in the construction. The r is with the dA. It's part of what makes the area. But when we go to integrate, the function we're integrating is r times f of r theta. Not just integrating the function of r and theta, we're integrating r times f of r theta. And then the description for the integration part is the same as we did before. What's theta between? What's r between? Or in this case, what's r between and what's theta between? Because polar coordinates have give a lot of different options for describing a point. Polar coordinates, unlike rectangular coordinates, which are two distances, since one of the coordinates is an angle, there's a lot of ways that we can describe a point in space. Unfortunately, there's like an uncountable infinity of ways we can describe a point in space. Yeah, there's a countable way. There's an infinite number of ways we can describe a point in space. And that can start causing some problems. So we generally agree for setting up double integrals, we're going to keep r non-negative, and we're going to make theta between 0 and 2 pi. If we let theta go from, say, 0 to 3 pi, we're going to count that upper first, second quadrant twice, and we don't want to do that. So for double integral purposes, keep theta between 0 and 2 pi. And let's keep r positive, non-negative. Doesn't mean we can't set up a double integral with things before 0 or after 2 pi. But if we know the unit circle from 0 to 2 pi, we know the circle everywhere else. So we're good. Let's just go from 0 to 2 pi for our descriptions. Now, this only seems like a lot to remember because it's a lot to remember. It's actually not that much to remember. Functionally, all we have to do, the TLDR here, is that include an R in your double integrals when they're in polar coordinates. You can think of it as part of the dA, but you're going to integrate it along with the function. Then you got to remember when you're setting up your integral that we keep R non-negative and we keep theta between 0 and 2 pi. Unless there's some specific reason that we want to double count some of those areas. How's everybody okay? Just after I get through saying, let's worry about one circle from 0 to 2 pi, I immediately remember that I have a quadrant 4. Ignore this part. We're going to keep R positive to not double count things, but I mean, the first example, the one that I was intending to do this whole time, is in quadrant 4 and quadrant 1, and I want to connect those. And the easiest way to do that is to use negative values of theta. I guess I have not recovered from yesterday. I wasn't contagiously sick, so don't worry that I'm here standing in the room. It was more kind of an injury sick, and it was less injury that something happened and more just, well, something did happen. Time has passed and components break down. It's like you keep a car going for a long time, but there are certain things that no question you're going to have to replace. Your brakes are going to have to get replaced. Your tires are going to have to get replaced. Most of your bushings and stuff like that, your suspension bushings, that's going to have to be replaced. There's nothing you can do about that. Hopefully, all the metal around that stuff holds up. but all the soft, squishy bits are going to break down over time. The problem is with the human body, everything is soft, squishy bits. It all breaks down over time. You never know what's coming next. Anyway, what are we talking about? Oh, yeah. Clearly not recovered because my first example, even as I was writing it, it's like, well, keep theta between 0 and 2 pi. Michael, that's in my back of my mind, I was like, well, that's a trig thing. Just keep r non-negative. I'm just going to write it anyway. And in the back of my mind was like, oh, all right, go ahead. Tell me what happens on the next page. And right now, the back of my mind is going, I told you so. So we want to describe what the volume under this function and above this region in quadrant 1 and quadrant 4, where we're going to need some negative values of theta. So we had set this up in the past with rectangular coordinates, and we found that was decidedly inconvenient. So we're going to set it up today with polar coordinates. So our function of x and y is 4 minus x squared plus y squared, because we're just going to start with a point at 0, 0, 4, and then subtract a larger circle as we fall down. Our function in polar coordinates is going to replace the x squared minus y squared with r squared, because that's the relationship between x, y, and r. X squared plus y squared is equal to r squared. So start off at, our function is still communicating the same thing. Start with this point and subtract bigger and bigger circles. So when we go to set up our double integral, I'm going to integrate 4 minus r squared. That's my function. But the dA part has an extra factor of r. That's what's going to turn d theta into a distance so that dA will be an area. So that red r there is included to be part of the dA, so that d theta will be distance, so that dA will be area. Now, the convenient thing that we've got going on here is that because our region is circular, our describing the region is just going to be a couple of intervals. We just got to describe what theta is between. Theta is just from here, negative pi over 2 to positive pi over 2. So down here is where theta is equal to negative pi over 2. And up here is where theta is equal to positive pi over 2. Here's where theta is equal to 0. We don't care about that right now. We just want theta to go from down here at negative pi over 2 up to positive pi over 2. Now, when we split this up, it's not going horizontal lines or vertical lines. Remember, we're using different graph paper. We're splitting it up like this. This is how we're counting these thetas. Those are all the different thetas, counting around the circle. Now, r is going to go from 0 to 2, the radius. So down up in here is where r is equal to 0. And out here at the end is where r is equal to 2. And I want this for every value of theta. I want r to go from 0 to 2. Every value of theta, I want r to go from 0 to 2. Theta is going to go from negative pi over 2 to pi over 2. Thing we want to notice here is that circular things In polar coordinates, circular things are described with two intervals. In rectangular coordinates, rectangular things are described with two intervals. In polar coordinates, circular things are described with two intervals. This is different from rectangular coordinates, where rectangular things are described with two intervals. What this means is that when we go to integrate, since we're integrating over a couple of intervals of constants, I guess they're always intervals, but constant intervals, our integration is going to be much simpler, which makes sense. The whole point of doing this exercise, the whole point of coming up with this additional description was that describing round things with rectangular coordinates is a bad fit. So let's describe round things with round coordinates. And that's all we've done here. So if we wanted to integrate this, I can look at this function as 4r minus r cubed. So we'll integrate that with respect to theta or r. Might be easier to do r first. Let me write the r integral. Actually, it doesn't matter, they're both intervals. But let's write the r theta integral anyway. My subconscious mind demands symmetry and completing sets. Mechanically, it's no different. But in my mind, I was doing this one first. So we're going to read 4 minus r squared times r as 4r minus r cubed. So we integrate with respect to r, and we get 2r squared minus 1/4 r to the fourth. And then I need to evaluate that from 0 to 2. We still have an integrated d theta. But let's continue our definite integral here. So 2 times 2 squared minus 1/4 of 2 to the fourth minus 2 times 0 squared minus 1/4 times 0 to the fourth. And we still have not integrated d theta, so let's remind ourselves that we have not integrated d theta. So this is all going to be constant. Here's 0. I've got 2 cubed is 8. Minus 2 to the 4th is 16. Divided by 4 is 4. So we get 4. And so we can see that we're integrating a constant function from negative pi over 2 to pi over 2. So we're integrating a constant function. We're just going to get 4 times the length of the interval from pi over 2, from negative pi over 2 to pi over 2. Or if we're like, oh, no, we got to integrate because integration is so awesome and fun, we'll have 4 theta evaluated from negative pi over 2 to pi over 2. So that'll be 4 times pi over 2 minus 4 times negative pi over 2. Which is the same 4 pi that we got previously. Because we had used rectangular coordinates to model this round stuff, and it was super inconvenient, we had to do the super inconvenient method of trigonometric substitution. Now that we're using the proper coordinates, round coordinates for our round stuff, the integration, the mechanics worked out much easier. There's also the d theta dr integral, which we would integrate the other direction. In this case, I've already multiplied in the r from the r d theta. But now we'll start with integrating with respect to theta. So I'll have 4r theta minus r cubed theta, evaluated from negative pi over 2 to pi over 2. Notice that we're going to be plugging in the theta. Keeping unable to leave things alone. So, but notice that we're plugging in for the theta. So plug in pi over 2 for theta, not r. And that'll be the last point that I want to make. All right, so that's it. When we're integrating, when we're setting up double integrals in polar coordinates, our dA needs an extra factor of r so that d theta will become a distance. All right, that's it for today. I will see y'all on Thursday because tomorrow's a flex day, right? That means there's no class. I'll put an announcement because I'm like, I was 100% sure that tomorrow is a flex day and there aren't any classes. And then as soon as any classes, and as soon as I said that, I'm like, I dropped down to like 98% sure. So I'll make an announcement. So I will see you on Thursday, most likely. I'm only 98% certain of that. Everybody have a good day. Once again, sorry for being out yesterday, and thanks for playing.